Hi, I want to show how we can derive expressions to allow us to calculate the magnification factor of a spherically curved mirror, as well as an equation to determine the location of an image with respect to an object. So here we have a slice of a spherical mirror, and we have a line running perpendicular to the exact center of our spherically curved mirror that we call our optical or principal axis. And we have an object out here that starts along that principal axis and extends to some height h. And that object is a distance p away from the plane of the mirror. Now, it's not a plane mirror, and this shows some clear curvature, but we're going to operate under the assumption that the actual curvature of this mirror is going to be very, 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 very small. So the differences between the location of this object and the location of the mirror are going to be slight over the size of the mirror. Now, there are two easy things that we could calculate without having to worry about where the normal is going to be. One, we could take a light ray coming from the top of our object that passes directly through the center of curvature of our mirror C. And the center of curvature is going to be exactly the radius of curvature, capital R, of the mirror away from the mirror on the principal axis. That means then that the normal is directly along that ray, so any light traveling from the top of our object through the center of curvature is going to bounce out directly along the same path. Now, the other ray we'll consider is one that goes from the top of our object and it hits the principal axis right at the plane of the mirror, which means that the normal is the principal axis, so the angle that that light ray comes in is the angle that light ray reflects, and where those two light rays come together, we get an image. And since these two light rays are coming together in real space, this would be a real image. Now, the equations we're about to work out apply for real and virtual images, but it's easy to show the trig just looking at the real case. So, the first thing that I want to do is I want to take a look along this green ray, bouncing at the center. Now, where the green and red ray intersect, we get an object that would start at our principal axis, go to that intersection point. Well, our image, I think I just said object, I meant image, is something that's flipped upside down. So real images from a single mirror end up flipped upside down. Now, the height of that image we're going to call h prime, and the distance from that image to the plane of the mirror is going to be called q for our image distance. Well, if I take a look, this angle theta has a tangent that's equal to the height of my object divided by my object distance p. The tangent of that angle is also going to be equal to, well, this object is upside down. So an upside down object would have a negative height, so the tangent then would be minus the image height divided by the image distance q. And that angle is the exact same angle. So that means then that h over p, the object height over the object distance, equals negative h prime over q, the image height over the image distance. So if I rearrange the ratio just a little bit, I can say that my image height h prime divided by my object height h is equal to minus my image distance q divided by my object distance p. And that is equal to the magnification factor m. So, for any image, the image height divided by the object height is the magnification. So if the number's greater than 1, it's enlarged. If the number's smaller than 1, it's reduced. If the number is negative, then it's flipped upside down, and if the number is positive, it's right side up. So an image height is positive if it's right side up. An image height is negative if we observe it upside down. Now for image and object distances, an image distance is positive if it's something that exists in real space. If we can actually form this image on a screen away from the mirror and actually physically measure that distance to formation, that's a positive distance. Now sometimes we have mirror images that are virtual. They exist only when we look in the mirror. They aren't existing beyond the plane of the mirror over here. Well, we can't really measure the distance from the mirror to where that image happens to be, so that would be a virtual distance, and virtual distances have negative length. So if we have a virtual image, we'd have a negative value for Q. If we had a virtual object, we would have a negative value for P. But real object, real image, both of those distances in this case are going to be positive. Now, let's take a look at the other triangles that we have. If we take a look along this red line, we get two triangles that have the same angle, alpha. So here, the tangent of alpha is going to be the height of my object divided by my object distance minus my radius of curvature, P minus R. Here, the tangent of my angle alpha, well, I have this upside down image, so I would have minus the image height divided by this distance here, which is my radius of curvature R minus my image distance Q. So the tangent of alpha is h divided by P minus R, which is minus h prime divided by R minus Q. Well, if I want to get rid of h and h prime, I can do that using my magnification equation. H prime over h is minus q over p, so q over p then would be minus h prime over h, and minus h prime divided by h is going to be equal to r minus q divided by p minus r. And that's equal to q over p. The image distance divided by the object distance is the radius of curvature minus the image distance divided by the object distance minus the radius of curvature. That's a little awkward and unwieldy. And with a little bit more algebra, we can actually make this look a lot prettier. So let's start by getting rid of denominators. So if I multiply both sides by p, then on the left-hand side, my numerator would end up being p times r minus q times p. And then I'd have a q hanging out over here. Let's get rid of this denominator by multiplying by p minus r. So that just leaves my numerator behind on the left, and on the right I get p times q, or q times p, minus q times r. Let's lump our positive terms together by moving our negative terms around, getting them out of the way. So if I add q times p to both sides, I'm going to get 2qp on the right. If I add qr to the other side, that's going to give me qr plus pr equals 2qp. And even that is a little bit more alphabet soupy. Now normally I'm not a big fan of fractions, but we can actually clean up a lot of these because if you notice, pr missing q, qr missing p, qp missing r. If I divide by qp and r in all of the terms, then I end up getting the term that's missing p is 1 over p, 1 over my object distance. The term that's missing q, 1 over q, my image distance. 1 over my object distance plus 1 over my image distance equals 2 divided by my radius of curvature. And that distance of 1/2 the radius of curvature is special. For a concave spherical mirror, if I send in light rays parallel to my principal axis, those light rays are going to reflect through a point that is that distance of 1/2 the radius of curvature away from the plane of the mirror. And that point where they focus is called the focal point little f. So for a spherical mirror that has inward curvature, concave curvature, the focal distance is going to be 1/2 the radius of curvature. Now on the flip side, if I have a mirror that curves outward, a convex spherical mirror, then light rays that come in parallel end up diverging, but it looks as if they originate from a point that is 1/2 of the radius of curvature inside the mirror. It's not a focus, it's a virtual focus. It's sort of doing the opposite of focusing. And that virtual focus would have a negative value. A real focus has a positive value. Distances we can actually sort of measure with a ruler in the real world, those are positive values. Things that we could infer from doing careful line drawing, but can't measure physically, those are always negative values, existing inside the optics only, through the looking glass.